Okay, number 9 here in 4.4 is asking you to determine the intervals on which this function is concave up or down. So that's what I'm calling the intervals of concavity here, and also to find the points of inflection. That's not really two different things, guys. It's really one and the same. All right, so what are we going to do? If we want to get any information about the concavity of our function, we are going to need to find our second derivative, which we can't find unless we find our first derivative. So here we go. Y prime, I'm going to get a little lazy with my shorthand right here. As I'm looking at this, I could do the product rule here, but that usually makes life a little bit harder. Then on the next step, I'm actually thinking we could probably take the time to distribute that x here in the original function and make that an x squared and then minus. Now remember, guys, this square root of x is x to the 1/2 power, and if I multiply that by x to the first, that would become an 8x to the 3/2 power. Now I've got that all written out in expanded form, and I don't think I have to worry about the product rule for either my first or my second derivative. So I think that's going to be the much easier way to go about finding our derivatives here. So if I'm following what I have in red there, my derivative, my first derivative, is going to be a 2x, and then minus, let's see, 3/2 times 8 is going to be a 12x, and we lower the power by 1, so that would be a minus 12x to the 1/2. There's our first derivative. Our second derivative then would be a 2, and then minus a 6, x to the negative 1/2 power. And I think it's probably worth it to take the time to rewrite that second term there. So this would be a 2 minus. Now remember, guys, a negative 1/2 power means I'm going to make a square root in the denominator, but that negative 1/2 power does not apply to the 6. It only applies to the x here. So the 6 is going to remain where it is in the numerator, and then we'll have a square root of x down there on the bottom. Okay, so that's where we're at right here, guys, and I think that's the best version I can come up with of the second derivative. So I want to know, where is this thing equal to 0, or, at the same time, let's think about this, where is it undefined? Let me go with that second part first. Anytime you've got a square root in the denominator, we know it would be undefined if the denominator were equal to 0. Now, they told us at the end of this problem that x had to be greater than or equal to 0. That's a statement that probably didn't need to be made, but they're just trying to help you guys out. Because of that square root there, we obviously can't put in negative numbers. However, what I do want you to notice here, though, is because of the greater than or equal to, 0 is in the domain of the function. However, guys, it is not in the domain of the second derivative because it would give us a 0 on the bottom right there. So I'm not going to worry about x equals 0, and if that's the case, I don't think I have to worry about this derivative, second derivative, being undefined. But I do think I need to worry about it equaling 0. So I'll bring that negative term to the other side and make it positive, and then I'll just swippy swap these two right here. Okay, so I now get the square root of x is equal to 6 over 2, which is equal to 3, and then we'll square both sides here and get x is equal to 9. No plus or minus right there, guys. We squared. You only need a plus or minus when you're undoing an existing square by taking a square root. So it looks like that's the only spot that we came up with right here where our second derivative is going to equal 0. Now, with that, that is the only potential point of inflection we have, so I'm going to make just a nice, simple two-interval sign chart here, and let's see what that looks like. I got to pick an x value less than 9, but still is in the domain of this function here. And I'm trying to think of what I'm going to do with this. I'm going to put it back into my second derivative, probably this form of it right here. So for that reason, I'm looking at what I'm going to need this x value to do. I want to pick a perfect square, just so I don't end up with anything too complicated. So I'm going to choose x equals 4. You guys, that is in the domain of the function, and it's going to be pretty easy to evaluate here. And then, picking something bigger than 9, I again want a perfect square, but it's got to be bigger than 9, so I'm going to go with 16. So let's go into the second derivative now, y double prime, with these two test values. So if I put that 4 in for x down here, square root of 4 is a 2 in the denominator. 6 divided by 2 is 3, and 2 minus 3 is negative 1. So the value of this second derivative is negative, which means we're concave down on this interval. And then, if I put a number bigger than 9, like 16 in here, let's see what happens. Square root of 16 is 4. There we go. 6 divided by 4 is 3/2 or 1.5. And 2 minus that 1.5 is going to be a positive 1/2. Positive, and we're now concave up. So I think we now have the answer to everything they wanted here, guys. If I go back up here and take a look, they wanted the intervals of concavity and any points of inflection. So I think we can now say, I'm not writing this in a good spot, but we can now say that our curve is concave downward on the interval from, we said 0 was the lowest value right here of the domain of this function, and that goes up until right here when x is equal to 9. Good news, everybody, you don't have to think hard as to whether or not these are going to be parentheses or brackets. The AP test will give you full credit for either one of them, and as a general rule, we tend to use parentheses right here, but if the book has it in brackets, that's fine too, not really a big deal at all. Okay, so it's concave down on that interval, and then we would say it is concave up on an interval, let's see, concave up starting here at x equals 9, and there really is no upper limit to the domain of this function, so that's going to go to infinity. So there you go. We've answered the intervals of concavity, and now we can also say, because there was a change in concavity right here, we have a point of inflection at x equals 9. So those look like the answers to the 3 questions they asked us for. Intervals of concavity, meaning where is it concave up, where is it concave down, and then do we have any points of inflection? So that's number 9.